Yay, okay. Okay, so a little bit of history to this. It's actually a presentation a long time in the coming. I started making candy sugar at home probably, it's almost 3 years ago now, only to later learn that what I was doing was totally wrong. And I also know there's a lot of myths out there about candy sugar and so on. And then I actually started researching what was it I was doing wrong and why. And this led into a whole, I started reading research papers, stuff that are not even beer related, and it became really, really interesting. There's other parts about beer that we also talk about in day-to-day terms, like Maillard reactions and caramelization and so on, which there's a bit of a myth around it. And my idea was to actually talk about that and maybe demystify the stories around all of this. So if I can go to the next slide. I think this is working. Yay. So what are we going to talk about? We're going to start with sugar, the different types of sugar, how this affects fermentation, how do you brew with sugar, what sugars, and then we're going to go into some biochemistry, and really it might get a bit complicated, so if it gets too boring or complicated, just stop me. If you think I'm saying anything wrong, I'm not a biochemist. I don't actually really know what I'm talking about. I'm just going to try. Then I'm going to go and talk about Maillard reactions, caramelization, and some biochemistry around it. And hopefully, once we've done that, we'll move into the actual making candy sugar, which I'm hoping is a quick part of the process. Okay, so put on your biochemistry caps. So we're going to think about beer from a sugar perspective. So there's a lot of stuff in wort when you make it, but actually from the sugars, we start with glucose and fructose, sucrose, maltose, maltotriose, and those are really your fermentables. So glucose is what we call a monosaccharide, and it's got chemical formula. If you can see my mouse here. So sugars are always in this formula, C6 or CNH something, O something, and that's a carbohydrate. So carbohydrate is always of this formula. When the M and the N are the same, it's actually called a sugar. Glucose has other names called dextrose, blood sugar, because it's actually the sugar that's in your blood, and corn sugar, because when you create sugar from corn, it's pure glucose. Fructose is what you find mostly in fruit. They make wine from this, and it's called an isomer of glucose, meaning if you look at the molecule and you swap things around a bit, it's the same carbon, hydrogen, oxygen, except it's swapped around a bit, so it's actually a different molecule with a different taste. I don't know if anyone's ever tasted glucose, dextrose. You can buy this. It's also called brewing sugar. It actually tastes a little different to the next one called table sugar. So sucrose is a disaccharide, meaning it's actually a combination of glucose and fructose. And this is found in cane and beet, and this is really where we get all our sugar. Pretty much 95% of all sugars you get is actually a form of sucrose. Sucrose is actually unique in that it's a non-reducing sugar, meaning it cannot make further chains and no larger chains of sucrose. And there's other reasons which we'll come to later on, which make sucrose quite unique. So if you think of it from a tasting perspective, sucrose is sweet, but glucose is a little bit sweeter, but like in a soft way. They make ice cream cones with pure dextrose. It actually tastes softer. The big one in wort is called maltose, which most of your sugars, and that's actually glucose combined in big chains. And this is really where it all starts. You get called a disaccharide, meaning it's two glucose molecules, maltotriose, which is 3 glucose molecules, and so on. At some point, they are no longer fermentable. When it gets too big, yeast just cannot ferment it, and then they're called dextrins. So maltotriose is a little bit of a funny one, that some yeasts can ferment it, others can't. So fully, partially fermentable, and so on. And this is actually where your fermentability comes in with different yeasts. There's other sugars I thought I'll just mention here. Galactose, you don't get that in beer. You find it in dairy, but you also get it in human blood. And then if you take galactose and glucose, then you get lactose, which is unfermentable, as we all know. So dextrins are your larger ones, and these aren't just, you can imagine like a really long chain. These are really your big sugars that yeast can't ferment, but they are all sweet. And this is where another sort of myth comes from. People actually believe that malt flavor comes from sugar, whereas all these sugars only taste sweet. The type of sweetness differs, but it changes. Also interesting here, dextrins are polysaccharides, but polysaccharides don't always have to be combinations of different sugars. They can be combinations of different carbohydrates. Polysaccharides get really big. So they split into 5 different main parts of nature, and you can say 95% of all carbon-based life on the planet are polysaccharides. Glycogen is what you store your energy in your body for most animals. The same thing is called starch in plants. When we mash, we actually break down starch into sugar. It's actually, we all know this. Structural polysaccharides are called chitin. They mostly make up plants and many animal harder skeleton bodies. Cellulose, most of your bones, cells and stuff are formed of cellulose. When your cells get too big and filled with that, then it starts looking bad and you have cellulose. So if that's too much biochemistry, just wait, there's more. So here's a little picture of what glucose and fructose look like. And then sucrose is bound in a sort of, if you swap the two around, you can sort of make out how they're bound together. You need water to break this barrier, and you need water to join the barrier. And we'll talk about more of sucrose and glucose later on. Okay. So what about yeast fermentation? So yeast fermentation takes sugar and it turns it into ethanol, carbon dioxide, and energy. And this is basically what we call fermentation. And what's really interesting when you read about this is actually that if you think that yeast ferments the smallest monosaccharides first, but actually it's sucrose that gets fermented first. So why? It's actually because yeast cannot ferment it inside its cell walls. So what it does, it first releases something called invertase, which is an enzyme, and you actually get this inside mash as well, which is why your sucrose is so low in the mash. So invertase actually breaks down glucose into fructose. And it's done outside the cell wall. And this is a really interesting fact about fermentation, because you actually need a lot of yeast cells to first do this, because the yeast cell needs to create an enzyme in order to break down the sucrose first. But these things also happen at the same time, and it depends on the yeast, on how picky they are. So you could say like some yeasts prefer to eat their greens first and then their steak, others eat a little bit of each at the same time, but it really just depends. So then they go for the monosaccharides, then the maltose, and then the maltotriose, and the fermentability really differs. And then they start struggling. And we know a little bit about yeast. So there's a gene called the SDA13 gene, which we call a diastaticus. And there's some like saison yeasts. They've got an extra enzyme which they produce due to this gene called glucoamylase, and they can ferment even some really large dextrins, and that's why the attenuation is so high. Another one, which yeasts I hate, called glucophilic. It means they prefer glucose first, and you see this in the Devel and the DuPont strains. They eat all the glucose and fructose first, and then they stall on you. If you've ever used the DuPont strain made a Saison, it tends to stall at 1035, 1040. It's literally because there's no more easy sugar for it and it's sitting there deciding. It'll eventually ferment, it just takes ages to actually switch from its greens to eat the steak now. Another interesting thing about this is if you've got too many monosaccharides or disaccharides, especially sucrose, too much sucrose, it makes the whole fermentation difficult. So if you're going to use easy sugars, use glucose. Buy dextrose and use that. That thins out your beer. You're actually too much sucrose, and they usually say about 10%. Above that, if you use sucrose, you're putting a lot of stress on your yeast, and you can account for that by increasing your cell count. But if you're using the same amount of cells, then you might find that a bit difficult. And then you put Brettanomyces and Pediococcus, and they change everything, and they can actually ferment dextrins that no other yeast can. Okay, so here's a little graph of how yeast ferments, and this is a typical fermentation. It's not, different yeasts differ, as I was saying, but you'll usually find after about 3 days, all your glucose is gone, all your fructose is gone, and your maltose, it takes about 4 to 6 days to finish. I would say it's probably usually a bit quicker. Your maltotriose, I think that's just some yeast ferment at all, some will touch it a bit, some will not touch it at all, and the dextrins, not at all. Another important thing to remember is that the remaining sugars, the dextrins, are only sweet. They add body and sweetness, nothing else. What we call malt flavor is actually from other compounds, and that's what we're going to talk about later. So sugar, how do you use sugar? Why do we use sugar? We increase the alcohol, we lighten the body. This is especially true for Belgian beers. Interesting flavors and aromas, and that is really what we want to talk about here. And priming. How do you add it? There are many, many different schools about how you add it. You add it to the boil, it's really easy. You can add it during primary. This is usually if you let the yeast ferment, actually start touching the maltose to a large degree, then add the remaining sugars, then you actually don't produce that stress. So if your original gravity is above 1060 or 15%, then it's probably better to add the sugar maybe later in the fermentation. How I do that usually is you boil some sugar in water, cool it down, and then just add it into primary after day 2 or 3. It works with really high alcohol Belgians, with other beers, maybe barley wines, doesn't really matter that much. Some people add it in secondary. This is really true, like if you want to use sugar that's got a really subtle flavor. I know maple syrup, people usually do this. They add it in the secondary, and then you actually get more flavor coming through. Or you can add it during bottling. Okay. So, list of all sugars, and you'd actually think the world of sugars is actually really complicated, where it's actually quite simple. So dextrose is the one we know. We call it brewing sugar. It's not many shops sell it. Table sugar you buy everywhere. In Europe, they usually make that from beet. You go to the States, they make it from cane. You get malt extract and DMA. Maltodextrin, this is really interesting. They sell it as something that's mostly dextrins, but I actually think it's not got 95% dextrins in, because I actually do get attenuation from them, and I actually think it's probably in the range of 50 to 70% dextrins, and the rest is actually smaller sugars that are fermentable. Lactose, we all know. Honey, we all know, and honey, that's a whole world of different honeys and different flavors. Maple syrup is an interesting one because Americans love making their maple beer. And this is what it consists of. And you'll notice that sucrose comes up a lot. Molasses, and that's the real interesting one, is molasses is actually one name for a whole group of different sugars, everything from brown sugar, piloncillo is something you get in Mexico, demerara, turbinaro, muscovado, and blackstrap. It's basically unrefined sugar. They mostly, if you want to get top quality molasses, you use the cane sugar derived versions. When they make something from beet sugar, it's usually not as good and it doesn't taste as nice. Most of the top chefs will only use cane sugar molasses. Golden syrup and treacle, this is an interesting one in that it's actually partially inverted sucrose. So inversion is the process of breaking sucrose down into glucose and fructose. So it's partially inverted, so it's got a sort of mixture of sucrose, glucose, fructose. Treacle is exactly the same thing, except you're doing it with molasses. So that's why it's black. So the quality of your treacle depends on the quality of the molasses you're using. So the taste you get from darker sugars that have unrefined products, it really just depends on what unrefined products are. Your thick molasses like blackstrap, half of the unrefined products is actually ash, which would probably taste terrible by itself, but can taste really good if you put it in a stout or something like that. Other sugars, I've got them at the bottom here because the main event, like I'm going to talk about, we've got caramel. There's an old one called Essentia Bina, which they used to make old porters from, and it was mentioned in Randy Marsh's book, Radical Brewing, so I thought I'd just mention it here. Jaggery, which is palm sugar from India, agave, made from the agave plant, and then there's various lots of other syrups as well. Candy sugar is, however, unique. Candy sugar is purely made for brewing, and it includes Maillard reactions and caramelization. No other sugar has this, and this is really what this is all about. Okay, so now we're going to move to chemical reactions involving sugar. And if I'm boring you, you don't have to worry. It's going to get a bit complicated, but then we'll make it easier soon. So there's three main reactions we talk about in sugar. Is inversion, and that's really simple. It's changing sucrose into glucose. You need water to do it. So if you leave your table sugar standing, it's not gonna invert itself. It happens faster at higher temperatures and lower pH, meaning acidic reactions. And it also occurs enzymatically with invertase, like we were saying. Maillard reactions, so this is really complicated and it's actually really badly understood. It's non-enzymatic reaction between amino acids and reducing sugars. And this is really where it comes in, amino acids. There was a biochemist called Louis Camille Maillard in 1912 who described it, but it was actually only in the 1950s when people started using Maillard reactions to create better bread, even steak, and understanding beer better. It creates literally thousands of new compounds with different flavors, different aromas. Your smell of steak, cookies, biscuits, everything comes from Maillard reactions. A good example is a doppelbock. Doppelbock, you could almost say, is a celebration of everything you get from Maillard reactions. Why do I say that? Because it's different to the next one called caramelization. Caramelization is, you don't need amino acids. It's actually just what they call a pyrolytic process where sugar just breaks down. You can have a high pH or a low pH and it literally starts falling apart. When it falls apart, it actually starts changing its structure. So together with water, you have condensation and then it loses the water, you have dehydration. Isomerization, what we were talking about, creates isomers. So you actually have molecules changing shape. Fragmentation, they fall apart. Polymerization, they form long strings. Cyclization, that is one of the interesting ones. It forms these little loops where the molecules actually become stable. And because these things, they happen and then they break down and they form a new molecule, they break down again, and it actually, what you get in the end is actually only when you stop the reaction. But it's the stable molecules that you're really interested in. and it actually overlaps with Maillard reactions. And this is what we're going to try and understand today, is what is the relationship between caramelization and Maillard reactions, because we often talk about we boil, we'll get lots of caramelization, we'll boil, we'll get lots of Maillard reactions, and the truth is both are true. So caramelization, you could say it's more caramel, hence the name, toffee, chocolate, roasted flavors. It's not a rule, but those are the sort of, if you think a stout and a wee heavy, that's the sort of flavors you're looking at. Okay, so I'm going to more focus on Maillard reactions because you can derive and learn a lot from caramelization while talking about Maillard reactions. So one of the interesting things, and they're poorly understood. What we do know is that they happen faster and a higher pH. And this little graph on the left here is actually a measurement of fructose and lysine boiled at 100 degrees. The lysine is an amino acid. Of amino acids, you get 19 types in beer. I think overall in nature, you get like 500 types. I think there's 22 different types found in humans. They make up the building blocks of proteins. What are they? Well, let's talk a bit about biochemistry. So you've got a functional group, which is this R here. You've got a carboxyl group and a nitrogen group, and it's this nitrogen molecule which makes it unique. You will create complex molecules with nitrogen in them through the Maillard reactions because of nitrogen in amino acids. Without the nitrogen, you'll only have caramelization and you'll only have your oxygen, carbon, and hydrogen. Other amino acids have other things like sulfur as well. What this shows is really what this graph here has really showed me what makes candy sugar unique, in that you've got fructose and lysine reacting at really high pH, and it's a really high pH of 12. It's literally minutes, and you've got everything is reacted and gone. The products of that is also what we'll talk about. So this is really what goes in, and then measurements of what's depleted afterwards. The main thing you get from Maillard reactions are called melanoidins, and you might have heard of melanoidin malt. Munich malt also has a lot of them. Melanoidin malt's often called Munich malt on steroids, and it's really what they are. They're trying to increase the amount of melanoidins. These are really large molecules. We don't really understand them that well. They give color and toasty flavor to beer. They also oxidize easier when hot, but they've got an anti-oxidizing effect when cooler. And we'll talk about beer aging and all these reactions as well. They also are a catalyst for high alcohols. You only get melanoidins in dark beer. In light beer, the lighter they are, the less chance you'll have melanoidins, because to create them, you need Maillard reactions, and then there's a lot of browning going on. So really, we're talking about dark beers here, malts. You talk about your standard toasty sweet malt flavor, that's melanoidins. The Maillard reaction, you start at a very high pH, and it happens fast, but the reaction itself then lowers the pH. Okay, so this is the most complicated part of the whole thing, and I'm going to, so please bear with me. If it's too complicated for you, don't worry, you don't need to understand anything that goes on here. There was a really good article here, which I put at the top, called The Science of Maillard Reactions, all in relation to beer. When I first read it, I thought it's too much, but actually stick with it and you actually start understanding a little bit. So if we've got amino acids, so if you look, this is really all the reactions happening. At the top, you've got aldoses and ketoses, and that is an aldose is really glucose, and the ketose is actually fructose. So those are the only sugars you got in beer that actually do this, but these are general names for different types of carbohydrates as well. You add an amino compound, then you get Amadori rearrangements. You don't need to understand what this is, I learned, but you can basically say the molecules rearrange in a certain way such that they break down even further when you add water. So when you add water, you create things called reductones, and these are larger molecules. They are fairly stable. Reductones, dehydroreductones. So everywhere where you see these minus amino compounds, plus amino compounds, this is really where you have Maillard reactions. Where you have little signs like this is actually caramelization of sugars breaking down. And the sugars break down into fission products and also reductones and dehydroreductones. So you could say there's different stages. The first one, stage one is it happens and it just breaks down your sugars into various parts. You could say the glucose, it's the same atoms, but they're in different shapes, in so many different shapes, they're unrecognizable. This stage is irreversible and it happens in a high and a low pH environment. Stage two, which we call is dehydration, fragmentation, and amino acid degradation. This really one, number E, is the important one. This is what we call Strecker degradation. And this only happens in a Maillard reaction. And it only happens for most Strecker degradation only in a high pH. And this is where Maillard reaction is really very different to caramelization. And these create what we call Strecker aldehydes. And these aldehydes are quite stable. I don't know if it's too small, but I hope everyone can read on the top here. The typical amino acids actually then sort of convert into Strecker aldehydes. So Strecker aldehydes have certain flavors and aromas. Some of them are malty, fruity. Some of them are green, floral, vegetable-like. Others can actually smell like paint and petrol, depending on which one. And each has a different flavor and odor threshold. They're different to esters in that they probably contribute more to flavor than aroma, but a lot of that malty aroma you get is actually this one, 2-methylpropanol, is very, very common in a lot of beer. The third one, this is really where the fun starts of your Maillard reactions. Oh, another one to mention here is called furfural. So furfural is unique in that it's an aldehyde, but it's a one-way system and you don't need amino acids to create it. Furfural was used by a lot of brewers to actually measure whether or not a beer has a stable flavor or not. And they still do this. If you actually take a beer, you can measure furfural by just shining some certain frequencies of light on it. And if it shines red, there's lots of furfural. It means your beer is not going to taste the same in 6 months' time. It means there's a lot of Maillard reactions that have not completed. So if you've got lots of furfural in your beer, it means the whole reaction has not gone down to the bottom yet. And it means the other parts are probably also not finished. It usually happens in brewers where the boiler is not quite as strong, or they have boils that have really, really hot areas, and they've got lots of caramelization happening in the boil. They call this heat damage to wort, and they measure this through furfural. Furfural is not the cause, but they've noticed that this is a sort of thing they use to measure how stable a beer can be. When we get to the bottom here, it's called aldehydes and nitrogen-free polymers. And these are really badly understood. But one of the most common one, not in the graph here, are called heterocyclical derivatives. And there's so many articles about this, it's actually quite bizarre. And these are actually a lot of your malt flavors you get from beer. So you can talk about beer flavor in terms of furanones, pyranones, thiophene, pyrols, pyrazines, furans, with flavors like cereal-like, cooked, roasted, toasted, meaty, maple, vanilla, sweet. All of those flavors are actually these things, the heterocyclical derivatives. The other one, the nitrogen-free polymers, are actually just your nitrogen-free version of melanoidins. which are really large, complex polymers. We don't understand them. We know there are many different types. We know they might have many different flavors, but we don't actually know how many or what they are and the variation. All we know is that they are stable. So these last three in stage 3, these are really your stable products that you get out of the Maillard reaction. Where do we get this? We get it from malt. We get this in the boil. We get it through many different parts. You even get Maillard reaction while the beer is aging. I thought I'll mention a little bit about aldehydes, because when you hear the word aldehyde, the one that always jumps to mind is the one at the top here, acetaldehyde. So acetaldehyde is not a creation from the Maillard reaction because it's not a Strecker aldehyde. Strecker aldehydes have a circular formation because they're stable in this big reaction. Acetaldehyde is linear. So linear aldehydes are generally not that enjoyable, and you want to keep them away from your beer. And they're usually created through oxidation or through yeast stress. So acetaldehyde is the big known one. The most common is formaldehyde, which is the smallest version of aldehyde. You don't get in beer. You definitely don't want it in beer. It smells and tastes terrible and used as a solvent. These ones, methylpropanol, methylbutanol, you can actually find them. They described in, so the descriptions often vary depending on where you look. The grainy varnish, I think when it goes above a certain threshold, it smells like varnish. Larger ones here, it has flowery smells, which is quite unique. It's actually something you're doing just with sugar and amino acids, and then you end up with flowery notes in the dark beer. Cooked potatoes, watery. Then there's the famous one, which is the most notorious aldehyde in beer, called trans-2-nonanol. This one has an infamous flavor of cardboard and paper, and yeah, you guessed it, it is responsible for oxidation in beer. And it's a reaction between another type of acetaldehyde and an oxidation of certain fatty acids, as I understand it. And here's the one, furfural, I was talking about. It's an indicator of flavor instability. It itself actually tastes quite nice. It's like caramel. So when we talk about malt flavor, these are the things we're actually talking about. It's actually quite bizarre when you think about it. And I actually think these things have really bad names. Wish we could have easier names to talk about. So now if we come back to Maillard reactions, this is probably the part we want to know, is what is the difference in the reaction? So Maillard reaction is sugars reacting with amino acids, and caramelization is just sugars breaking apart and reforming. The flavors, usually when we talk about malt flavor, it can be anything from bready to nutty to toffee to roasty, but actually, if you start thinking about it, there's bready, sweet, fruity, toasty, nutty biscuits versus caramel, and I say nutty because this is actually where there's a crossover. Coffee, toffee, chocolate, roasty, and I'd even put like rum in there as well. It's probably more on the caramelization side. Temperatures, and this is where they really differ. Maillard reactions happen at really low temperatures, but they take months to years. So when you put your beer down to age, Maillard reactions are still happening, and you might actually get a very different malt profile 6 months down the line, and the temperature you keep it at actually matters. There's a lot more happening in your beer than that because of yeast also doing its stuff and hop oils and so on, but at least when it comes to sugars, Maillard reactions are happening. Caramelization, probably not at all. The higher the temperature, the quicker it happens, up to a point, and there's a sweet spot here at about 135 degrees to minutes. When you go over 165 degrees, the caramelization is basically the sugar just falling apart. Those reactions we were talking about just cannot happen anymore because the caramelization takes over and it's just too fast. For caramelization, it actually differs per sugar. Fructose is really fast, it's 110 degrees. Sucrose and glucose at above 160 degrees, not actually sucrose. They say it here, but actually sucrose first needs to, because we were saying it's a non-reducing sugar, it cannot go through caramelization or Maillard reaction in itself. It first has to be broken down into fructose and glucose. Maltose at even higher degrees, and that goes through caramelization directly, and lactose even higher. What's even interesting here is Maillard reactions happen faster and at higher pH. And this is also where candy sugar is different. You make it at higher pHs, not at lower pH. And that is where I was going wrong all those times. I thought we make the sugar acidic, and then we're going to make candy sugar. You're not. You'll make something, you can create caramelization, but you won't get the complexities that you do from Maillard reactions. The thing is, you can actually have both. You can actually have Maillard reactions and caramelization all in one, as long as you sort of step it through. The resulting compounds, this is what we're talking about: melanoidins, aldehydes, perfluorol, the heterocyclical compounds. It's not actually the heterocyclical compounds, it's actually their derivatives. It's something that's combined to them. The compounds themselves are actually poisonous, which is interesting in themselves. And it's also, there's been books about how beer is actually carcinogenic, and it's all about certain furin is actually carcinogenic to you, but it usually binds with something else and then creates these lovely flavors that we love and call beer. Caramelization, I'm not going to talk about that in too much detail, but there's some other stuff called maltol, which is one of the toasty flavors which we love. It also creates diacetyl. A lot of that just gets boiled off and is not as stable. It's actually one of the fission products we were talking about earlier. And then there's oxygen heterocyclical derivatives, and there's much less of them. Lactones is another one which has got a rum flavor, and you only get those at really high flavors, and you also get that in barrel-aged beer. Oxidation, this is really interesting. Melanoidins, they oxidize when hot, and they are antioxidants when cool. Caramelization, in general, the products have an oxidizing effect. So you might know this if you use a lot of dark caramel malt, your beer is probably more prone to oxidation over time. This is oxidation when cool. It's also, there's this sort of hot side oxidation story. And my theory is, and this can't be proven, is that hot side oxidation mostly happens when there are lots of melanoidins within the malt. So hot side oxidation is only really relevant when you've got a lot of, say, Munich or melanoidin malts in your malt bill. Otherwise, it's probably not as much of a matter. That's just a theory. Maybe there's more happening. A lot of people say hot side oxidation is a myth, but that's a theory of mine and unproven. I don't know. Effect on color, and this is the one thing. If you want melanoidins, it has to be dark. Caramelization, it happens so fast it gets black. It gets black within minutes. Black malt is a proof of this. It's actually caramelization that we're getting. And that's why where we get all our color from beer comes from these two. I thought I'll just mention here, this all sounds really complicated, but actually when you look at, this is labs, talk about malts and oxidation in our, we've got this on our website. You can actually see, I think it's a total guide to all beer, all flavors or something like that. If you go to oxidation, there's a whole lot about melanoidins and a lot of what I've been talking about here. So if it seems like what I'm talking about here is a little bit strange and weird, it's actually, there's a lot mentioned here. Aldol condensation, Strecker degradation has actually all been mentioned in beer or flavors under oxidation. Quite interesting. You could say maybe brewers need to know about this more. I'm not so sure. It's probably something for the geeks. So if you want more Maillard reactions or more caramelization, what do? Maillard reactions is decoction is probably the most common one. It creates more melanoidin. Some people say you don't need it, you just add melanoidin malt. True. in my experience, I love decocting, and I feel like I get way more complexity doing it. I think it's because the sort of complex melanoidins you're getting are just, there's more types of them when you actually decoct with adding the melanoidins. If you add melanoidin malt, you're just taking the subset of melanoidins that they define in the malt, and you're just using the same thing that every other brewer does. You can actually get more complexity, a much more unique beer if you actually decoct yourself. Again, this is unproven. It's just one of my opinions, but in my experience, I love decocting, especially a doppelbock. You can boil, and it's the thing about this is that water is usually at quite a low pH. So you will get Maillard reactions, but they're just certain things. The Strecker degradation just doesn't happen. You'll get Maillard reactions, but only a small subset of them. So you won't get the complexity of Maillard reactions that you do get from boiling longer than you would through, say, decoction or using melanoidin malt. Also, it's at 100 degrees, so it's not really happening that fast. Malts you can use, Munich, Vienna, melanoidin, they're the most common known. Aromatic is actually, it's a crystal malt where they actually, the start was a Munich type malt. So you can actually say it's got a lot of Maillard reaction type. Caramunic is the same, some lighter crystals, they've got Maillard reactions, not by design, but purely by accident, just because they're, it's at lower temperatures. I'm not an expert in malts, but this is my understanding. So if you want more caramelization, a longer boil, but this is really interesting, how your boiler is shaped and how strong your flame is, what your contact surface is, and if you've got one large flame on a small surface, you're probably going to have more caramelization than a smaller flame over a larger surface. So some brewers actually don't like this, that they actually use they use steam going through pipes because they don't want the caramelization in their boil at all, especially British brewers making bitters. It creates a much more stable product when there's less caramelization, less furfural. So our shape of our boiler actually makes a big difference to our beer, and even if we all made the same recipe, we might actually end up with something very different, a large part, because you get caramelization happening in the boil. What malts, you can use darker crystal or roasted malts, and we do this all the time, and it's all about actually adding caramelization products to our beer. Or you can sidestep both of these and you can make your own candy sugar, and this is where so I'm going to stop all the complicated stuff now. I'm going to talk about candy sugar. Why is it unique? It's because it's the only sugar out there of everything else that actually contains Maillard reaction and caramelization products that you can actually buy off the shelf. If you think the Westvleteren 12, which is rated one of the highest beers in the world, is purely Pilsen malt and candy sugar. Candy sugar is purely made for beer. The Belgians have a sort of state secret on it that they don't want to tell you how it's made. We sort of know how it's made because we know it's got lots of Maillard reactions and caramels. I see I've lost a few people, but that's okay. I understand. And it adds aroma and flavor, but it also thins the body. I find it actually, it's quite boring because they standardize it across the industry. So they're trying to make a candy sugar for lots of different breweries. So you end up with quite a boring result. I've tried to use different candy sugars. Whenever I add it, it's always just the same thing, which made me start thinking like, hold on, maybe if I make my own candy sugar. There's an American company, I think, called Candi Sugar with a Y, and they actually make different syrups. It's difficult to find here, and it's quite expensive to import. I think they call it the D180, measured by its color. And that is actually candy sugar made with a very specific flavor and Maillard reaction caramelization in mind. There's lots of myths around candy sugar. Lots of people will tell you it's the same as inverted sugar. Inverted sugar is just sucrose changed into glucose and fructose. It might have other unrefined bits in it, but it's not the same as candy sugar. Some people think it's purely to add sugar. I think the light candy sugar is, or purely to add alcohol and thin the body. The light candy sugar, I think it is. It's once again the Belgians just selling you something. You only really have the Maillard reactions and caramelization if it's dark. If it's light, it's just not in there. Some people think it's the same thing as table sugar. It's not. And this is what we're going to talk about. And it's also easy to make at home. And this is what's really, really interesting. I think us as home brewers don't do it enough, because we actually have opportunities to make flavors that are just not possible. You can't buy this stuff because of all the secrecy around it. And in my experience, I've made some really interesting sugars that I actually end up adding to my coffee even, just because each time I do it is different. And so let's start. What do you need to make candy sugar? You need a large pot with high sides, and I'd say a large pot because you're going to have splashing hot sugar, and this pot on the side is probably not big enough. I'd probably go for a tall pot if you can. Sugar thermometer is an absolute must because you want to actually maintain the sugar at a certain temperature. You don't want it to go too high. A long spoon, a pastry brush, that's actually, if there's crystal sugar on the side, you want to just rub it off. I say eye protection and long sleeve shirt and gloves maybe. This is all just for safety. I've had splashing sugar fall on my skin, and it's at 140 degrees and it's sugar, and it'll keep burning until you get it off. No, it's not fun and it's dangerous. You can have a pH meter, but you don't have it. It's nice to measure the sugar afterwards. So first of all, we're going to look at inverted sugar. So this is purely making sugar that's inverted from sucrose to dextrose and fructose, what we were talking about. I go for a 1 kilogram recipe. You usually dissolve that in 300 to 400 milliliters of water. You can add an acid because it actually happens faster in an acidic environment, but usually the sugar itself creates enough acid for it to happen anyway. If you add acid, it just happens faster. Dissolve it first. So if it's not fully dissolved before you hit boiling point, you're actually going to have crystals, and you're not going to actually have the reaction happen as you want. This happened to me once, and I actually stopped the whole thing, had to cool it down, add some water. So literally add to like 80 degrees, stir until it's all fully dissolved. It's actually really weird how a kilogram of sugar dissolves into 400 milliliters of water, but when it's warm, you'll notice it just does. Stir. Brush off the crystals, like I was saying. And the important bit is hold at 100 to 110 degrees. And you might remember earlier we were talking that fructose actually starts going through caramelization and Maillard reactions above 110 degrees. So you really want to keep it below 110 degrees and anywhere from about 10 to 40 minutes, and the reaction starts happening. You end up with something with glucose, sucrose, and fructose. If it's more acidic, you'll probably have more glucose and fructose. When it gets too hot, so you're sitting there with a pan, I usually added like 1 or 2 tablespoons of cold water, and this actually cools it down. So 2 tablespoons in this recipe usually cools it down easy to 3-4 degrees. So you go up to 110, down to like 105, and you keep there. And it literally means you have to stand over it. And this is really where it's tedious. It's not like brewing where you can actually leave it, you actually have to stand there. Sometimes you can actually find a smaller flame on a gas hob, but you can actually find a sort of stable point where the temperature is not going up. But over time, there's so much evaporation, it starts warming up anyway, and you have to stand with it. You shouldn't have any browning. If you have browning, it's now going into the Maillard reaction stuff. It means you probably went over the 110 degrees. Once you have it, when you cool it down, you just add water. If you add enough water, you can actually create a syrup. I actually like the syrups because they're really easy to add into the boil. If you just let it cool, it gets rock hard. That you need to then break apart, and to add that in the boil, it sinks to the bottom and it can actually burn on the bottom of your boiler. Syrups are just better. And you literally just add water as it cools. You can actually keep it in the fridge. It will thicken. You can keep it in the fridge for 6 months. You can make it now and use it whenever you need it. When you want to add it to a fermenter, you can just heat it up again to sanitize. Okay, and now candy sugar. So this is the next step. So the real difference between candy sugar here are these two. It's the same recipe, but you want to add an alkaline and amino acids. If you don't add amino acids, you're not making candy sugar. So amino acids come in many forms. They come in wort. DME's got amino acids, and lots of yeast nutrients has amino acids. You don't need a lot. You literally need a tablespoon with a kilogram of sugar. Even that, some people say, is too much. Then you need an alkaline because you want to increase the pH. They say you increase it to about 12, but anything above 8 will be okay. I don't know. I think varying pHs will actually change the reaction and you'll get different flavors. So the process is you actually first create inverted sugars. If you use stuff like golden syrup instead of table sugar or lots of dextrose, then you actually don't need to invert first because you want glucose and fructose. You don't want sucrose. So once you've got lots of glucose and fructose and you've inverted, you raise to about 130 degrees and you literally keep it on a hot flame and you just raise it. Once it hits 130 degrees, stir, 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 keep stirring. Then you add your amino acids and alkalines. And this is a little bit of a careful point. The alkaline, it splashes up when you do it. It's something about when you raise the pH, it really splashes. Be careful. I've burnt myself a few times doing this. Once it's there, you'll find the whole sort of texture of it changes. It's not just sugary, it's not just water with sugar anymore. It almost looks like a dough syrup after that. And that actually means the reactions are happening and it's a good thing. And you can keep stirring. At this point, it's usually quite light. You can leave it at this temperature and just keep stirring, 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 and it just gets darker and darker and darker as you create more melanoidins and you get more browning. So it's literally just standing there, and it's quite tedious because you have to stand and stir. If you leave it, you get scorching, and it can actually boil over, or it can, if the temperature goes too high, then it literally starts, you get caramelization. It turns black in 5 minutes easy. And the whole thing is then a black mass of caramelized, what do you call it? Black candy sugar, and you won't get it off your pot. You can, however, add caramelization. I've done this once. I raised it to about 160 degrees. In 5 minutes, it was so black, I stopped and it really boils up. How they do this commercially, I think it's in a closed environment. It's quite dangerous. Usually I don't think they do this commercially because most candy sugars are not black. So you can if you want. It also happens at a high pH, but I actually think black malt will do you instead of the Maillard reactions you're trying to get from candy sugar. Just a warning of danger. I don't want to tell anyone what to do. Do not leave unattended. It tends to boil over. Keep cold water at hand if it falls on you, or just throw cold water on you, as you don't want this to happen. If it falls in your eye, you can lose an eye. So use eye protection, maybe some sort of sieve that goes over it, and keep stirring. So some pictures. I was going to do a video, but then the video sort of failed. But this is the sort of pot. This is after 5 minutes, so this is actually still inversion. And you can actually see the bubbling looks a bit different. So this is inverted. after 5 minutes into the candy syrup. So this is after 15 minutes at 130 degrees, and you can already see it gets a bit browner. So this is not adding an alkaline, but you're already starting to get some Maillard reactions, even though it's in an acidic environment. So this is after adding DME, and not just DME, but also an alkaline. And you can see it gets this sort of funny texture, almost like a pudding, I would say. I've got a little picture here. It's like after every 10 minutes, then I sort of take a little drop and just put it out, and then it cools down in minutes and forms a little crystal. Actually, to get this off this plate that I put here, I had to pour boiling water over it. It literally just doesn't come off. Very tasty and very enjoyable. I was planning to do this meeting and actually bring some candy syrup that I made, let different people taste. If you do them at different temperatures for different lengths, you really get different flavors. What really stands out is the fruity sweetness, and I don't think any sugar's got this. It reminds me of a sort of a doppelbock versus a barley wine. It's got this fruity maltiness versus a sort of caramel maltiness. And that's really what makes candy syrup unique. Okay. Once we've got that recipe, we can actually vary it. And there was this guy, there's a blog called Ryan Brew's blog. He actually did this. It's really interesting for someone to go through so much effort just to prove a point. So you can change the alkaline. The one I use is called pickling lime. You can't buy this in America because it's illegal, but over here they don't mind. They just post it to you. It's actually, if you dab your finger to rub your eye, you can lose an eye from it because it's so alkaline. And even a teaspoon of it, they say just try and be careful with it. But it's probably the most alkaline that thing you'll get. You can use lye, which is sodium hydroxide, baking soda, which is sodium hydrocarbonate, or chalk, which is limescale, is calcium carbonate. I actually think different alkalines will give you different flavors, and this is what this guy was saying at Ryan Brews. Different amino acids using DME, yeast nutrient, or even wort itself. You just need a source of amino acids, maybe something else that will actually give different amino acids will definitely give you different flavors, as we saw from the graph. So actually changing even different types of yeast nutrients will give you different flavors. So this is all very interesting. We can try different things, different recipes. And in the future, there might actually be different recipes for the candy sugar you use to make your Belgian quadruple. Even try different sugars. You can try unrefined sugars as well, which lots of people do. Then it's almost like cheating in a way. You get a dark sugar even before you start. Different temperatures, the length of the boil, the length of your inversion, and even varying the quantities or additions. Play around. This is really what you're doing. What really stands out here is that he just used the lime. So that means he's not adding amino acids. So even after 40 minutes, he gets a sweet, minerally, slightly chalky flavor. Here he just adds baking soda, the malic acid, just an acid. Here's an acid and a nutrient. So here he is actually adding amino acid, but he's doing it at a low pH in an acidic environment. This is really interesting. He gets a burnt sugar bitter flavor. And this is what I've had. You'll find most people, they do it in a bitter environment, and the sugar they get is quite tangy. I wouldn't call it bitter, but you get this sort of tangy, acrid maybe flavor. It's not that nice. You put it in beer, those flavors are not that apparent, but you're not actually adding anything to the beer. However, when you add the nutrients and the lime, and this is also lime and nutrient, so you're increasing the pH, then you get toffee and dark fruits. Over here, you get fruity, strong, dark caramel flavor. These are the ones we want. The two ones that we put in color here is actually the type of things. So the important thing is increase the pH with an alkaline and definitely add an amino acid, but which those are doesn't really matter. Okay, getting to the end of it. I'll stop talking soon.
Sorry, Jack, just on
Yes.
that table,
Mm.
sorry, the two coloured ones, what was the difference between them? You got lime and nutrient, and the other one says treacle and nutrient and lime.
Yeah, so when you add lime, you increase the pH, so it's an alkaline. The lime is an alkaline, where the others, so chalk is just adding an alkaline with no amino acid. An acid in the nutrient is only an amino acid, but no alkaline.
But what's the difference between the two that you've coloured in?
Well, the one used treacle and the other one used just table sugar.
Right, okay. Okay.
Yeah. This is not my table. But this
No,
is
I'm trying to understand it.
Okay.
Cool.
I think I'll take questions now. I'm sorry for talking so long. I get really geeky about these things.
Well, my other question was going to be about the for your amino acid. So you've got DME and you've got yeast nutrient on there. Is there any difference between them? Is there any benefit? Because I mean, the cost difference between some DME and some yeast nutrient by weight is quite different. What's the benefit?
Okay, you're only using a tablespoon. So yeast nutrients actually has quite a variety of amino acids, but the amino acids are there for yeast health. The ones within DME are probably the same that you get in wort, which means you get the whole lot of them. I'd probably say you get a bigger variation in DME. Yeast nutrient, they won't tell you. You might be able to find it somewhere, you don't know. Some yeast nutrient, it's called diammonium phosphates, DAP, and that's actually something else that's in the yeast nutrient. Some yeast nutrient is pure DAP, and that won't work here because it doesn't have the amino acids. And they call it yeast energizer in some parts, but it's quite difficult to find. Most yeast nutrients have amino acids. The truth is, I don't know. I don't know which is better. I use DME because I thought you'll probably have the whole plethora of most amino acids. They'll give you the most complexity. Don't know.
Okay.
I've got a last one here, is how do you use this? So inverted sugar, it's literally just for thinning the body, creating more alcohol. We use this in blondes, golden ales, triples, saisons, cream ales. Maillard reactions, this is usually for doubles, quadruples. I'd say partially for Scottish ales. It would go lovely in German styles, but they don't allow you. Doppelbocks are actually a celebration of Maillard reactions, but they do that through their malt, not actually through sugar. Caramelization, we use this a lot. In old ales, barley wines, wee heavy, stouts, we do that through malt, and we do that through sugars as well. Okay. Any more questions?
Wow.
Yeah. I'm really sorry.
I am positively loaded with information. Can I start brewing now? That was awesome. Thank you.
That was amazing, Jack. That was very cool.
I sort of lost count on how many different ways were there to lose an eye in that. I think I counted 3.
Rob, there's a drinking game.
Yeah.
Has anyone done this? Has anyone made candy sugar at home? Yeah.
Yeah, I did. Yeah, it does work. The thing about putting the alkali in, like a huge game changer. Like it's almost instant, and you can smell it. It's amazing.
Yeah, totally agree. You actually, while you're doing it, it's totally, that is the difference. Yeah.
Yeah, I've baked a Russian honey cake a couple of times, and what I was actually doing is adding baking soda to honey, and the mixture looked exactly the same, like that bubbling, sticky, moussey thing. But I had no idea it was my reaction. But yeah, the flavors you produce from honey and baking soda are like miles above the actual honey itself, and that is the key to making a Russian honey cake.
Wow. That totally makes sense, because you do need water for the Maillard reactions, and if you heat that up, it'll probably happen quicker. Yeah. Wow.
Yeah, isn't that how they make like the children's honeycomb sweet as well? It's literally just sugar and baking soda.
Yeah.
Cookies. cookies, biscuits, it's all Maillard reactions. Even steak, it's all Maillard reactions.
Now I want steak.
Yeah, broccoli doesn't have that.
Jack, that was really good. A lot of it went over my head, except when you got down to the end, condensed it all down to the making of it. Absolutely fantastic. Can we commission some and pay for it? First question's, as it's so dangerous. The second thing is, you sort of dismissed light candy sugar. Now, there are a lot of Belgian beer recipes I see using light candy sugar, and in fact, I was just about to make one. What is the benefit of using light candy sugar, if any, and do the Belgians use it in making their beer? And if so, why? Why not just inverted sugar?
Well, candy sugar is inverted. If they're making light candy sugar, they probably only go through the Maillard reaction step, probably only just for a few minutes to make it as light as it is. And yes, they do use it. They use it in triples, they use it in saisons and blondes all the time. It mostly has a thinning of the beer effect, but that malty flavor that you get, you just don't get it from, I mean, I don't taste it in the light ones. So if you're using it, it might actually add a little bit of extra flavor and aroma to a triple. I would say don't use table sugar because you're just adding extra stress to your yeast, whereas candy sugar is mostly dextrose and fructose. So just in that sense, it's better. If there's any difference in aroma from using light candy sugar versus dextrose, I don't know. Some people say there's none. Some people say there will be, but there's not much of Maillard reactions going on. But yes, use it in triples, use it in blondes, and don't use table sugar. You're just adding, unless you want to stress out your yeast even more. I think that's the message.
Okay.
What kind of percentages are you using the darker candy sugars, Jax?
So
What kind of percentages? What kind of percentages in a recipe, you know, are getting used for that?
Right. So if you make a really dark candy sugar and you add to like 5%, you will notice the flavor. If it's a lighter one, and go for about 10%, but then you're probably aiming for something like a double. You're borderline on thinning the beer out as well, in addition to just adding the flavor. Then you notice it. But if it's quite a light sugar and it's just 5%, the other malts in your beer will probably overwhelm it. If it's the only dark addition, if you're just using that plus Pilsner malt, then 5% will probably add quite a bit as well. Taste the sugar. It's actually amazing when you taste it, the same flavors you taste in the sugar, you do eventually get in the beer as well. The taste is similar to the aroma you get. For me, I don't know.
Okay, so it's probably akin to...
Anyone else have different experience? Think you should add more?
I've used up to 20%, I think, of the dark Belgian sugar, but you know, the shop bought, not homemade, and that came out mostly with caramel flavors rather than you know, kind of the complexity of it.
Sorry, I'll just stop sharing. Yeah. We call each other again.
I don't know for sure because I haven't done enough. I think if I use a lot of homemade candy sugar, I have to age the beer for quite a while for the flavors to sort of calm down a bit. Like
yeah, I found that as well. You need some aging, yeah.
Like straight out of the fermenter, you're a bit not sure what's going on there, but it settles well. Like up like 10 to 20%. Starts getting a bit.
Yeah, I mean, to be fair, the beer that I have made with that much sugar, I'm still, you know, it's dry. It's still being, you know, it's been aging for a little while. It's actually a quad, And I've used, just to confirm to you guys, I've used, yep, 19.3% of the dark candy sugar from Malt Miller's website. And I didn't think that that was too much, to be honest with you.
Yeah, I think I've used 20% candy sugar in a Belgian Golden Strong, and it was fine. But then again, that was the light candy sugar.
Yeah, I've diluted some of the dark candy sugar from Malt Miller just to see what it tastes like, and it was mostly sweet. There were other flavors like a bit of plum, a bit of like sort of like dried fruit, but it was mostly sweet, which is why I was actually looking forward to this presentation, because I don't really want to buy it. It seems to be boring and simple.
Jack, you mentioned the use of the pH meter, but you didn't mention what sort of expected pH you would get.
Yeah, I've not actually. I once measured the pH of my sugar and then ruined my pH meter because it got stuck, and then I added in boiling water, and then the pH meter just died on me. So I didn't really like doing that. You want the Maillard reactions happening at around pH 12. That's what they suggest. I don't think you need to go that high, but actually you just do it once, and then the actual reaction as it goes on reduces the pH again. So you can, they say, and like I say, I've not measured this, maybe someone else here can, you end up with a pH at around 7 and 8 if you leave it for about an hour, which is quite a dark candy sugar. So, I mean, I wouldn't want to add something really alkaline to my beer anyway, because you don't want to affect the pH too much. You don't want to go beyond your buffer of your beer. Yeah, so I don't think I know the answer. So yeah, the eventual sugar is not too alkaline because of the actual reaction.
Yeah, as you say, 7 to 8 pH is the same as water from your tap.
Yeah.
So.
Exactly. Yeah. I also think that's why when you do a Maillard reaction at a low pH, it makes it even more acidic. And these are these acrid flavors we get sometimes when you make, if you make inverted sugar and then just heat it up, then it just becomes really acidic. And that's not a nice flavor to add to your beer. Yeah. Those are the acrid flavors that you get. I think. I don't know. To be honest, I've played with this a bit, but I've not really done enough research. It takes about 2-3 hours an afternoon of doing it, and it's dedication. You really have to stand over it. Yeah. It's not just something you do in an evening. You have to prepare and be careful.
Yeah, if you turn your back on it for even a second, it will jump out of the pan and throttle you, I think.
So no drinking, because then you can't run to the loo.
Well, I wouldn't go that far, but yeah.
It's kind of like doing a whole brew day, like, like one of your first brew days as well, because, when I've done it about 3 times, and it was like I was always finding a problem, just like on an early brew day as well.
Yeah. Yeah, the more you do it, the more you have a process and you know what to look out for, yeah.
Yeah, I feel like there is a double waiting to happen.
So the other one they've spoken about, if you've ever made a wee heavy and then you sort of take some wort and you boil it separately. Some people do this when they make a wee heavy. I've tried it, and then it sort of boils down, and then as soon as it starts hitting the syrup, it really starts boiling up. And that's quite dangerous, I think. But if you get the flame right, as it boils up, you reduce the flame, boils up, reduce the flame, then it sort of stops boiling up. But if you actually do that and then add an alkaline, because you've got all your amino acids in the wort, add an alkaline, you can actually have a much more complex beer as a wee heavy than you would if you're just doing a straight boil separately. And this is a really interesting thing. You could make wee heavies with more complexity and Maillard reactions than people do. It might not even seem like a wee heavy anymore, because I find a lot of them actually quite, I should say, one-dimensional malty. But that's not true. Not all wee heavies, but that's just me again. I've not done this, but I thought about it.
I think it would be something easy to do in all those brewing one systems, because you have really high walls, so you can transfer some of the wort out and boil that smaller portion, and then just add the rest and just transfer to and chill and transfer to the fermenter.
Yeah.
That would work, right? Because you have plenty of space, big walls, and you can just boil it there.
I found it much easier to do it over a gas flame than in an electric boiler.
Okay.
Because the electric boiler just isn't powerful enough to get a really good strong boil going in a thick sugar solution.
Okay, yeah, that's a good point, yeah.
He did it for his wee heavy, is that right? Did a separate boil for some of them. Liamins did a separate boil for his wee heavy, I think.
I think Lee's done it, yes.
Yeah.
Yeah, I've boiled down about 5 liters of wort to maybe a liter, if that, and towards the end, yeah, it did rise up as a thick mist, but obviously the pH would have been way low. But luckily, no acrid flavors, but the intense caramel and all sorts of it.
Yeah.
So, Jacques, in terms of the Maillard and caramelization that goes on in our wort boil, electric heating element or gas flame underneath the pot? What's best?
I have no idea.
Okay.
I think I actually did ask myself this question. A flame from a gas hob is 1,900 degrees Celsius. The electric ones, I do not know. So if you think you've got a gas hob, what is the eventual contact with the metal on the wort? I think there's definitely a temperature where it's like 1,000 degrees on a few molecules. And just those few molecules actually do make a difference, because you don't need much. You really don't need many of these molecules to add a flavor difference. Electric, I really can't tell. How hot do those elements get? Does anyone know?
Well, it would actually depend on the element, because if you're looking at the low density elements, they would be cooler than the high density ones. And actually, the high density ones are the cheaper, because all it is a massive chunk of metal and of high resistance, and that's what actually hits your wort. The lower density ones are a bit more complex in their structure, and they have a much wider area, so you actually don't get any of that burn on, and that's, I think, what the higher end all-in-one units actually have, not the cheaper one that I got.
Yeah, I mean, I would imagine like taking the surface area of an element, and if you could sort of unwrap that and consider the surface area of it compared to the surface area of a pot. I would certainly prefer, if I was doing this, and I plan to do this, I think, it sounds a lot of fun, albeit dangerous. But I would think I would be better off using sort of a low flame with a larger pot, basically, and making sure that the sort of that heat was dissipated across the whole of the bottom of the pot rather than concentrated on an element. Because I've had an element turn black from boiling. I think I had like flour in the boil or something like that got through. It was a high wheat mash, and yeah, just scorched the whole lot. So with something a bit more delicate and volatile like sugar, wouldn't touch it with an element.
Jacques, you've kind of mentioned the boil length and Maillard reactions. What's the relationship there? Because obviously you're boiling at about 100 degrees where Maillard reactions aren't really happening, but they're still happening just at a much lower rate. So would you say then with a normal boil you would get a much higher Maillard expression if you boil that doppelbock for 2 hours? Say.
Yes. And I don't know, is it again the shape of your boiler that matters more and you get more caramelization? Maillard reactions are happening even though that your pH is around 5 and it's at 100 degrees. The Maillard reactions are still happening. So it's not a myth. That caramelization is also happening if you've got any flame or anything like that. But how much this is happening again is the surface area, the heat, and I think there's so many things at play. I really don't know. But yes, Maillard reactions are still happening in the boil, yeah.
So
and how much? Nobody knows.
So then how will a decoction give you a higher Maillard expression than a boil of ultimately the same wort?
A lot of it is because Maillard reactions, if there's too much water, I think I had it in the slide. If there's too much water, it slows down the reaction a lot. If there's no water, there's no reaction whatsoever. There's the sort of sweet spot of how much water. So a decoction reduces that amount of water versus the amount of sugars. And this is actually why the longer you decoct and you actually stir and boil the decoction, that is really where you're creating the melanoidins.
So that's why you pull the thick mash then?
A thicker mash creates more Maillard reactions than a thinner one. And then if you do it at home and you've got some scorching, you've probably got some caramelization as well. The two interact and overlap.
All right. Plenty more tools in the toolbox.
Yeah.
Got a question about, I think he said that there's Maillard products in loads of baked things, like you mentioned digestive, like biscuits. I was wondering, could you throw a bunch of digestives in into your mash and then get a similar effect to candy syrup?
So you think put biscuits in your mash?
Well, if you can get it, I mean, if there's Maillards in the digestive biscuits, it could be a cheap candy syrup.
Digestive stout, anyone?
Yeah.
Isn't there that Lithuanian beer where they make with bread? They actually make the bread first and then they put that in the mash, something like that. Don't know. Yeah, sure.
There are loads of butter in digestive biscuits. You probably wouldn't want that in your mash.
You're talking about kvass or something like that? You sort of made from old rye bread.
Kvass would use rye bread, yeah, which I guess would have very high Maillard reactions. It just kvasses then soured. So you get actually the complex malt, but sour.
It's a type of Lithuanian beer. It's on
like a Keptinus or something like that.
Yeah, I think that is the name for the standard. I'm trying to Google it.
The Keptinus you bake in the oven.
Shove in the oven, yeah.
Yeah, is that the one? Yeah. You bake it in the oven. Well, you bake your malt as a bread.
Yeah.
Yeah.
Okay. Right.
And there's a lot of chat there about like the water content of it and how thick you should pull that mash and what sort of temperatures, if you're aiming for caramelization temperatures or if you're not as well. So there's a big sort of interplay there of flavors.
Well, Rob, the one that you made a couple of years ago now, it tasted like gooseberry jam. It had the aroma and the flavor of gooseberry jam.
Oh, I'll pretend that was what I was going for.
No, like that's probably one of the more interesting flavors I've gotten, like from a beer I'm drinking without expecting it at all.
Yeah, I have no idea where that came from.
And it was also like a year old. I really kept it for a while.
Yeah. Mm.
Yeah, I remember having the one you brought to club night for BrewCon in the first year. and I pulled like quite a decent amount of that, and then was quite pissed. And I think it was like 7% or something like that. I found out later on.
You can do
But
that. Yeah, they're strong enough. I think
drank just like a bitter, basically.
Yeah, these farmhouse ales, they don't muck around.
I was reading how they make Munich malt. They actually, because it's a base malt, so you can actually, it's still got all the enzymes and everything, but they actually keep it at like 85 degrees with a lot of moisture for like 2 days. Whereas most malts, they actually kill and dry and immediately. Whereas with Munich malt, that's what makes it so different. And Vienna malt, I think, is at a lower temperature. Correct me if I'm wrong, but I don't know much about this, but they stew the malt at like 85 degrees. And that's really the Maillard reactions you get from that process from Munich malt. Yeah, there's a comment. Vienna is lower, so not so long.
Yeah, if you compare 100% Vienna against 100% Munich, Munich is a heck of a lot darker, a lot more melanoidin compounds in it. And it's actually quite an interesting experiment to do. Personally, I prefer 100% Vienna over 100% Munich.
Yeah, I'm not sure I'd want to drink 100% Munich beer, really.
Oh, no, 100% Munich Dunkel. Oh, that, yeah. That. Yeah, I'll have one of them.
Yeah.
Yeah, I'll have one of them, yeah.
Yeah, a Dunkel could work really well with it. Unfortunately, it was 100% Munich with some New World hop that someone did in the smash off, and it just didn't really work all that well.
Yeah, we had a smash competition. Was it last year or a year before? And a couple of people did 100% Munich, and those are pretty decent.
Okay, guys, I do have to ask: are we talking about light Munich or dark Munich?
I did 100% light Munich for an alt beer.
Yeah, that I can see. Dark Munich, however,
yeah,
I'm skeptical.
I
just said 100% Munich on the one.
Yeah, I used the standard Munich for Munich Dunkel, and then I boiled it for like, I think 40 minutes or 45, and the color was on the paler side, but it was still, kind of within the guidelines. So you can get quite a lot of color. Yeah.
I just did 100% Vienna lager as well. That was really nice too. I like them both a lot. The Vienna and the Munich's really nice.
Well, everybody, I've done very well, but I need to go and have my breakfast. And I'd like to thank Jack for his wonderful talk. I found it very interesting, and I wish you all well, and g'day.
Cheers for coming, Peter.
Hey, Peter.
See ya.
Yeah, thank you, Jack. That was an awesome talk.
Yeah.
Yeah, it was brilliant talk.